So this is double integrals in polar coordinates. And some objects sort of have sort of a radial nature where they just want to be a function. The boundaries want to be a function of theta. So what I'm going to do here is draw sort of a region with rays extending out from the origin like this, and boundaries like this. I don't like those boundaries very much. So I'm gonna make it better. Okay, so this is our region R. How do you find how do you integrate over a region like that? Well, let's say we have on the inside R is going to be like like a G1 of theta. I'm going to make that look better. Oops. On the outside, obviously, R will be G2 of theta. Okay. And then the limits on theta will just be from one angle to another. So on the lower angle there, you can say, let's say theta is alpha. And on the larger angle, let's say theta is beta. Okay. So we're going to be integrating in polar coordinates, and the thing is if you're going to use R and theta, then when you chop this region up, you have to use like constant values of R and constant values of theta. So what do I mean by that? Let me see if I can get a real light color here. So this is how you chop regions like this up. Actually, I'm going to just do a little extra work here and zoom in on this. I'm going to chop it up real nice with slices that come from the origin like this. You get the idea. And so those are slices in one direction. Of course, we have to slice it up two-dimensionally. So I'll also do slices this way. Now these are circular segments. And maybe we can just focus on one of these. So pick one of your bigger ones out and let's outline it. Okay, now I'm going to have an angle that defines this. Remember, the two coordinates are r and theta, so the differentials will be dr and d theta. So I think I can measure an angle here and maybe I'll go just to a little bit darker color and call this angle here d theta. But then the change in radius this way would be dr. And so the area of the region here we'll just call dA. I don't really want to write dA, so let's just put it off to the side. So dA now a differential area in polar coordinates. And what I do want to do is put the point right in the center of that, and I'll call that point r theta. Like that. And I need to find the formula for dA in terms of r and theta, because the point is that we're going to be doing a double integral with a dA in it because you're integrating over patches of area. And dA has to be converted just like it was in xy coordinates, where dA was dy times dx. But now dA has to involve r and theta, differentials in r and theta. And the problem is that you can't say that dA is dr times d theta. So I'll make this note. Because d theta is not a length. So because d theta is not a length, dr d theta cannot be an area. Does that make sense? Okay, so what I want to do, I think what I want to do is, I'm going to zoom in on this thing. So I'm going to copy a bit of this little guy and see if I can clean it up. And blow it up. So I'm going to erase a whole bunch of this and just preserve the one region that we're talking about. Okay, and I'm even going to shorten these lines here. Just trying to make a smaller, but something I can version, something I can blow up. So maybe just have a picture sort of like that you can draw on. Okay, so just to remind you, I want to do a length in both directions on this. So I need this length here. that's an arc length. And I need this length. That's easy. dr is this differential length. This green length is a bit of arc length, and we always use ds for arc length. Okay, and dA is going to have to be 2 lengths, so it's going to be ds times dr. Okay, let me go to a wider font. I'm going to clean that up a little. Okay, so you have to remember on a circle, there's a formula for arc length. So we'll do that real quick. Okay, so if you have an angle theta, let's say this angle that I've just highlighted is theta, and then this is the arc length that we're interested in, so that's called S, and the radius of the circle is R. Does anybody remember the formula for this arc length?
R times theta.
Right, S is R theta. Good, thank you. So when we say then S is R theta, then ds is going to be R theta. So, and R is not a differential. That's actually the distance to the origin. So it's just weird that you're going to have a differential that requires a measurement from the coordinate system. You can't know how big this arc length is without knowing how far it is from the origin. Okay, so in polar, you can just step back and say, all right, well, dA then has to be, it's ds times dr, but that needs to be r times dr times d theta. Okay, so this is the key to integrating in polar coordinates. You just have to remember that you always get an extra r thrown in because theta is not a measurement in terms of length. It's a measurement in terms of angle, but angle is not a length. It's not really anything. It's just a relationship between two rays. So dA is r dr d theta. You know in polar x is r cos theta. That y is r sine theta. You know that x squared plus y squared is r squared. And so if you have to integrate a double integral of f of xy dA over r, right, then this should be, at this point, pretty straightforward. You're going to change the x to r cos theta, the y to r sine theta. The dA has to have a length for theta, so it has to have an arc length for the ds. So you're going to have an r dr d theta, like that. Okay. And then you can say, then you can go back to the original picture up here. Remember, we had r going from g1 of theta to g2 of theta. Okay. And then theta went from alpha to beta. So those are the limits on your integral. So you'll have, oops, so r has to go, I think I said g1 of theta to g2 of theta, and then theta has to go from 0 to 2 pi. This is the normal order of integration in Polar. Any other order would just be insane. It's not that you can't do it, it's just that it would be a huge bummer to do it. So this is the normal order of integration, meaning you do R first and then theta. Okay. So I want to give you guys a second to ask the question if you like. We'll do an easy example and then a hard one. Oh, and by the way, yeah, that's it. That's all we got to worry about. We're good to go. Isn't it supposed to be from alpha to beta? Yeah. Thanks, Bilal. You're there for me. I appreciate that. I don't know why I did 0 to 5. I'm not thinking. Thank you, Bilal. All right, so that's just the general form. It's pretty easy to do. The only thing that's hard in this section is people don't like graphing in polar coordinates. And I get that for sure. Let's do an example. Okay, so here we're going to do a double integral over a region that we'll call R of cos of x squared plus y squared. Yay. That's just begging to be in polar coordinates. It depends on the regions and the region you're integrating over. R is a disk centered at the origin. With radius 2. First quadrant. Okay, so disk is easy. Okay. Now there's not an inner curve. If you want, the inner curve is a point. It's r equals 0. Okay. And I'm going to kind of think about those slices I was talking to you guys about. So I'm going to do slices kind of coming out from the origin. Like that. And then I'll put that little red differential area in there. I've got to move my R, I think. Okay, I'm going to put in my little red differential area, just a little teeny slice of area. That's my dA. And that little red differential area has to cover this whole region. So the coordinates of that point are r theta. Right in the middle of that is the point r theta. And to fill up this entire region, that's the job of this little teeny differential area. It has to fill up the entire region. And to do that, R has to go from where to where. This is almost too easy, but so we're going to have a, hang on, hold on. Let's do, what's the x squared plus y squared? It's r squared, right? So how about if we do cos of r squared, and then dA gets an r dr d theta? Any questions? Okay, and again, that little patch in the diagram has to cover this whole region. Its center is r theta, so r has to go from where to where? Right, 0 to 2, and theta obviously, and then once it goes from 0 to 2, then you've effectively filled up this whole slice. Only the slice though, by allowing r to go from 0 to 2. Now theta has to vary, so of course theta is right here, and for this red slice to cover the whole region, theta has to go from 0 to pi over 2. Okay. Yeah, so it's a pretty easy integral now. I'm just going to zip right through it. It's not uncommon to have constant limits on these. So on this one, I would say u is r squared, and 1/2 du is r dr. Okay, so let's see here. We're going to have a cos of u squared, which is 1/2 du, and theta. And if r is 0, u is 0. And if r is 2, u is 2 squared. So that would be from 0 to 4 now. And I do not want to use squared inside there, so my mistake. Sorry about that, everybody. Any questions? Just you. Thanks, Alicia. All right, so the half comes out and you just start plowing away. This is not pretty. Okay, so we get 0 pi over 2. Let's bring that 1/2 out. Okay, and the antiderivative of cosine is just sine. So you're going to have sine u. And u is going from 0 to 4. You know sine of 0 is 0. And so this is just going to be sine of 4. So I think we get a 1/2 integral from 0 to pi over 2 of sine 4, whatever that is. Don't care. D theta. And sine 4 is a constant, so you're going to have 1/2 sine 4 just times theta. Where theta goes from 0 to pi over 2. So I think in the end, you're going to get like a pi over 4 times sine of 4. These are not degrees. We always assume if you're integrating that you're doing it in radians. Pi over 4 sine 4. Okay, any questions about all of that? So that's a simple one. And now we have to do a hard one. Okay, here comes. This one just says find the area of the region enclosed by both cardioids. R equals 1 plus cos theta. And R equals 1 minus cos theta. Now, this is pre-calc, graphing polar graphs. And I think what I'm deciding to do is when you have a question about a polar graph and homework or whatever, just ask me. Okay? And I'll walk you through where the graphs are coming from. Otherwise, I'm just sort of going to give you the graphs because, you know, you have covered cardioids before, and they are called cardioids because they sort of look like hearts. So that's a cardioid. I don't know if it looks like a heart or something else, like a butt maybe, but I'm ashamed to say that, so I won't say it. Okay, so that's a cardioid. But there's two of them, so the other one's inverted. So I'm going to turn it over like this. It's not great. It's not great. I've done worse. Okay, so these are my two cardioids. On the right, you have R equals 1 plus cos theta. And on the left, you have R equals 1 minus cos theta. Okay. Your coordinate system right down the middle of all that, which I have not done a good job of, but I'll put this in position here. That's pretty good. Now it says the area enclosed by both cardioids. So there's actually two areas. We'll just find one and then we'll double it. So I'm just going to shade one of these. Okay. Honestly, there's a better way. And I know you guys are thinking it. I want to hear you say it. I'm gonna tilt this a bit because it's a little off. I don't know if I can do that. I don't know if it'll let me. I don't know if you've noticed. I'm moving things again. Sorry. Oh dang. Notability hates me. I'm not sure. That ain't bad right there. It's not good, but it's not bad. All right, so what instead, let's just do a quarter of this. Let's just do this much, and then we'll multiply it by 4. Okay, I almost don't know which side to go on, but that's fine. Okay, so I think I'm going to zoom in on that. So if we zoom in on it, you basically have a curve that just goes like this. Okay. And that's what I've colored in green there. And this is a cardioid that's mostly going off to the left. So that's the 1 minus cos 2 theta. Okay. And normally, again, I like to draw these radial slices. So if you think about it this way, kind of a radius array coming out from the origin here, and then another one coming out here. Okay. And the thickness of that angle is just d theta. But we'll put 2 little arcs inside of this. And this is our little differential area here. The point in the middle is, as before, that point is r theta. Okay. And the curve here is not the one on the right, it's the one on the left. It's 1 minus cos 2 theta. Not 2 theta, just cos theta, my apologies. Okay. Okay, so any questions about, so if we're just going to do the area, let me guess the questions in a second here. So area is just a double integral over a region of 1 dA. That's the formula for area now. And even to make it better, it's the area of R. So let's make that more clear. Let's say area R. Okay. But be careful, we're only doing a quarter of the region, which they're calling R. So let's multiply this by 4, because we need 4 of these. Okay, any questions? Okay, let's go straight into it then. So we're going to go 4 integral dA, which is r dr d theta. It always gets an r. Otherwise, it's not an area. Okay, limits for r. At the tip of the slice and at the outer edge of the slice. So I know what you're thinking. You don't want to type it. I get it. It goes, r goes from 0 at the tip of that little slice that I drew, that little pie-shaped slice, to the other end where r is 1 minus cos theta. So maybe I'll move this little indicator down here. That's where r is 1 minus cos theta. And the tip where r is 0. Okay, any questions? And then you have to measure out your theta angle. So I think I'll do that in blue like I did before. So this angle here will be theta. And then you just got to think about, well, what is the range of values for theta? And you just have to kind of think about, well, the fact that initially these angles are basically starting off at 0. You can't see them very well, but I'm trying to draw in a bunch of angles here to cover this region, right? So those angles down toward the bottom of this are where theta is 0, and then all the way up to where theta is pi 2. So it's similar to the last one. Okay, so feel free to unmute yourself and ask a question about this. Nothing. All right then, so let's go ahead and evaluate this monstrosity. It looks bad. Okay, so we're going to have 4 integral 0 to pi over 2. So we're going to have a 1/2 r squared, right? So 1/2 r squared, where r goes 0 to 1 minus cos theta. don't like the idea of integrating that. The 0 doesn't contribute, so you just have 1 minus cos theta squared d theta, where theta is going to range from 0 to pi over 2. Okay, any questions? I hate to think that we have to multiply that out. Here we go. So you're going to have 2, this is just a normal integral, so I'm going to pound this out real quick here. So you're going to have 2 integral 0 to pi over 2. Then you're going to have 1 minus 2 cos theta plus cos square theta d theta. Unfortunately, with a cos square, you're going to have to do a power reduction on that. So you're going to have a 2 integral 0 to pi over 2. So 1 minus cos, sorry, 2 cos theta is fine. It's the cos square, which you have to write as 1/2. And that's going to be 1 plus cos 2 theta. That's how you integrate cosine squared. So you're going to get trig integrals with cosine squared, sine squared, cosine to the third. Who knows what you're going to get? All kinds of crazy possibilities. I almost want to run that 2 through now to get rid of that half. So you'd have integral from 0 to pi over 2, and now you'll have 2 minus 4 cos theta plus 1 plus cos 2 theta. And 2 plus 1 is 3, so I don't know how many times I'm going to rewrite this thing. So 3 minus 4 cos theta plus cos 2 theta. Okay. And now we can integrate. Now this is the last term is just going to be 0 because the sine of pi is 0. Sine of 0 is 0. So here you're going to get 3 pi over 2. And then sine of pi over 2 is 1. Sine of 0 is 0, so it would just be minus 4. Let me know if you have any questions. Sine of 0, check your math. Cosine 0 is 1. What is KB? What is KB? My bad. What is KB? Kidding, bro. It means kidding, bro? Is that what you're saying? You're kidding? Kidding, bro. I'm going to use that. JKB. Just kidding, bro. JKB. Okay, I'm going to use that all the time now, bro. Okay, let's keep going. You guys okay? Sorry, you guys, I'm sorry. I don't know if you noticed, but I'm trying to be funny. You're not supposed to laugh. I know it's not funny. Okay. I was not being serious. That's all I want you to know. Okay, any questions? And Alicia says, just you. I was like, me? Who, me? Yeah, you. Let's go. You guys okay with that last one? Hey, wow, whoa, I am just me? You are too. Okay, going on. This is ugly, 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 but let's see if we can do it before our break. So this one says find the volume. Bounded between z equals 1 plus 2x squared plus 2y squared. And z equals 7. In the first octant. Okay, just a first octant, just think first quadrant, but it's above the xy plane. So x is positive, y is positive, but also z is positive. Okay, so 1 plus 2x squared plus 2y squared, that's just opening upward, paraboloid, my bad, with circular cross sections. So let's see what we can do here. Oh, great. Okay, now you're not going to get this whole thing. So, and also z equals 1 plus 2x squared plus 2y squared. That's not touching the origin on the bottom, so we got to be careful of that. And let's identify a point in the middle of this right there. And you've got a lid on this where z is 7. So this is sort of the top. Okay, so top is z equals 7. But then the bottom, it goes down to where z is 1. I'm going to put some dashed lines in here just to hide some things, make it look like they're hidden anyway. So I'm going to dash the z-axis because that's inside. The axis goes down a little further though, so let's have it go down. Just it's supposed to hit down where down to the origin, but the bottom of the surface is where z is 1. So maybe we can put a little dot down there and put a 1, maybe a 7 up here. First octant, so that's a little difficult. I'm going to draw these the xy axis. I'm going to make a little copy of it up above real quick. Ooh, let me do that. Copy it up above, just here, so I can see my first octant. Okay. So I'm going to switch colors to do something a little darker to make it clear that I'm not using this whole thing. So this is the part in the first octant. If not great, I'm sorry. Any questions? I'm going to also draw the shadow. So I can shade this. I'm going to shade it in a second, but I want to draw my shadow of this down in the XY plane. So just one sec here. Remember, if you're going to integrate over, dx, dy, or dA or whatever, if it's over the XY plane, you need to draw a shadow down there. So this is me trying to grab a shadow. I'll erase this stuff that I need. Okay, so that's the shadow. And move it where it belongs here. Yep. Okay, so any questions? So that region down in the XY plane is just R. I'm going to put a little R down there. That's what we're integrating over. So, and I don't know what the radius. That's a circle, but I don't know what the radius is. So, z equals 7 is the top. The parabola z equals 1 plus 2x squared plus 2y squared. The intersection is the boundary, so we need that intersection. I'll call that the intersection curve. Okay, where 7 is equal to 1 plus 2x squared plus 2y squared. You guys follow me on that? So that's x squared plus y squared equals, let's see, 6 divided by 2 is 3. So this is x squared plus y squared equals 3, I think. And so that's a radius, that's a quarter circle with a radius square root of 3. Okay, so I'm just going to pause a second, make sure you guys are all with me on this. KB, what does KB stand for? I never know. God, I hate that. All right, now, so it's just a volume between two surfaces, so you have to do the top surface minus the bottom surface. So volume, let me go with that. Okay, volume is a double integral of the top minus the bottom dA. Okay. Over the region R, you just have to integrate over the shadow. Okay. So let's see. The top is the 7 minus the bottom 1 plus 2x squared plus 2y squared. Like that. And dA. Any questions? Okay, and then double integral 7 minus 1, so that's going to be 6 minus, let's factor out the 2 from those. So let's say 6 minus and have a 2, and then an x squared plus y squared here. Just factoring that 2 out because that's going to be our r squared. So remember the x squared plus y squared, that's r squared. And dA is going to be another r, so that'll be r dr d theta. Is everybody okay? This is actually an easy integral now, if you look at it. So it's just 6 minus 2 r squared. And then we'll put the r, and then dr d theta. Okay. And then r, we can graph the region now, I guess. It's just in the first quadrant that we're integrating over. So I'm supposed to draw a quarter circle here. I'm just going to draw a full circle in the radius. Like that. Not good. There it is. Is there any question? So again, the limit here, I'll make it bigger, but we're just mostly interested in the limits for r and theta. And again, I always draw the same picture here, thinking about slices that go out from the origin radially. Like that. And a little patch of area in here that is centered at the point r theta in polar. Okay. And at the tip, r is 0. And at the other end, r is radius of that quarter circle, which is the square root of 3. And that little bit of area has to kind of spread out and cover this whole region. Okay, so you move it and let it go, let r go from 0 to the square root of 3. And theta from 0 to pi 2. Okay, any questions? I'm going to evaluate this pretty quickly here. No. Let's do this. Let's do this. This will be better for us. I want to remind you of a trick from the last lesson. And maybe I'll even copy this over. So hold the phone right there. I'm going to jump over to our last lesson that we were doing, which is 15.2. And remind you of, we had a list of kind of rules that we had talked about, and this is the rule I want right now. Okay, and so this is from your notes from 15.2. It says over rectangular regions only, that is to say where the limits are constant. So I'll update this as I paste it into the other lesson that we're working on. Okay, so this is all going to go under recall. a little large. Let me scale it down here. Now, I don't want to say rectangular in polar coordinates because it's different in polar. I would say over, let's say it this way, for integrals with constant limits. We'll say double integrals. And then I'll just say and a function of x times a function of y. This is just a kind of a principle that we laid down, and it's super handy. It makes it, I don't know, it just makes it faster. So you have to have constant limits, and then you have to be integrating a function of x times a function of y, and you can break that into two integrals. And I showed you where that came from, but it's not hard to show where it comes from. It's in the book, it's in the notes. But you can apply that to this problem because we have a function of r times a function of theta. In fact, function of theta is just 1. So you could write this as an integral from 0 to pi over 2. And there is no theta anywhere, so let's just say d theta. And if you want, you can put a 1 in there. And then times another integral from 0 to the square root of 3 of, well, if you multiply the r through, you're going to have a 6r minus 2r to the third. And now that's what I'd consider pretty straightforward integral. So obviously, this first integral is pi over 2 times the second integral, which I think I'm going to just let you trust me on this. It's 9 over 2. So the second part is 9 halves. So that in the end you get 9 pi over 4. Okay, you can check my work on that, but I think I checked it in Maple, so I'm pretty sure that's good. It's just basic integral. All right. So I'm just going to back up a little bit and wait to see if anybody wants to ask a question. Not seeing anything. In terms of questions out there, I'll just pause. And now I'm kind of flipping to see if there's another example I should try and squeeze in. It's already 7:30. You guys are probably ready to take a break. I'm going to do one more example after the break, but I'm not going to work it all the way through. I'm feeling a little nervous about the next lesson, which is a long one. And we will not finish it tonight, but I want to get started on it. So let's go ahead and take a break till 7:40. All right. And I'll see you back here in a sec. Okay, so now we're going to add one last example here. You guys all ready? Go ahead and write the next example down. The instructions are to convert to polar and evaluate. But we may evaluate this one without doing the calculus behind it. And so it's the integral from 0 to 2 on x, and then limits on y go from 0 to the square root of 2x minus x squared. The integrand is the square root of x squared plus y squared. Okay, so we need to figure out what this surface is. Down here, you've got, sorry, what the area you're integrating over is. Down on the bottom, you've got just y equals 0. And on the top, you've got y equals, you know, square root of 2x minus x squared. We need to figure out what that is. So I'm going to try and multiply everything out. You've got a y squared equals 2x minus x squared. That looks like a circle. We'll have to complete this square. You've got x squared minus 2x plus y squared equals 0. Adding 1, you get x squared minus 2x plus 1 plus y squared equals 1. So that's x minus 1 squared plus y squared equals 1. Okay, that's a circle. But notice that y is greater than or equal to 0 on this. And that would be true here as well. Y greater than or equal to 0. Because it's a positive square root at the top. Okay, so that continues to remain. So the region you're integrating over is a circle. Well, it's a semicircle. So let me draw the circle, then I'm going to erase half of it. It's centered at 1, 0. So up on top, that's the upper square root. So y is the square root of 2x minus x squared. Y equals 0 down on the bottom. I don't want the bottom of the circle, so I'll erase that. Okay, and then we'll just call that region R. Any questions? Kind of need to know what this thing is in polar. So let's see what it looks like in polar. When you have y squared is 2x minus x squared. I think we should put the x squared plus y squared together. So that's r squared is 2r cos theta. Okay, which I suppose you want to stipulate that r is not 0 before, we don't want r just to be 0, so we can divide it out and just say r is 2 cos theta. So that curve is also r equals 2 cos theta. Okay. Okay, so I think we can evaluate this integral. The dy dx is the dA. Square root of x squared plus y squared, that's just r. So let's see if we can do this. We're integrating r, and then dA, which is another r dr d theta. Okay. Now, if you're to do these radial slices that I always talk about, I might have to do a little trick here and get rid of that. So let me move this back. Move my R out of the way, and I'll put in my slices. Out to the edge of the curve here. Okay. And block out my little differential area. Okay. And the point is centered at R theta. So at the beginning, where R is 0, we have a point. So let's start it where R is 0. Okay. And then the outer limit is the curve, R equals 2 cos theta. I'm going to move these around. Just to make it a little more appropriate to the diagram. So R goes from 0 to 2 cos theta. Okay. And of course, our theta angle will have to go from 0 to pi. Okay. I think it's all I've got time for on that. So I'll tell you what the answer is. If you actually, I won't tell you the answer because I didn't work it out. I don't think I ever meant to. The final answer, integral 0 to pi, integral 0 to 2 cos theta is R squared, and we'll say dr theta. See that right now. And as I say, that's pretty much all we got time for. It's kind of important that you get this straight, so I try to do lots of examples on this. I want to go ahead and start the next topic, which is applications. And as I say, this is a big topic. We will not finish this today. I hope we finish it next time.
Teacher, why this?
There's a small mistake. We're going to fix the upper limit. Obviously, the limit on R needs to, sorry, limit on theta needs to go to pi over 2, not pi. Thank you so much for that. So we'll just fix that real quick. And that was one. Thanks for that. Does that make sense, everybody, that correction?